So in the last video, I tried to convert this very ugly looking integral, double integral in rectangular coordinates to something a bit simpler in polar coordinates. And I asked, can I just do this? Can I just convert everything over from x's and y's to r's and thetas and then treat it like the same integral? And the answer is almost. You need what I said was a Jacobian. And for going from rectangular coordinates to polar coordinates, this Jacobian is an extra r. All right, so if you throw an extra r in there before the dr d theta, then the answer is yes, you can do this. You need this little Jacobian, which seems sort of random, but a Jacobian is just a little bit of extra thing that gets kicked out whenever you change variables within an integral. And you're already used to this without realizing it. When you do a u substitution in Calc 1, you would come over off to the side and you'd say u is equal to 2x, and then you'd say du is equal to 2dx. And then if there wasn't that 2 in your integral, you would have to compensate for it with like putting a 1/2 on the outside of the integral. That 1/2 was the extra little bit that got kicked out by changing variables from x's to u's. Likewise, when we go from dy dx, rectangular coordinates, to polar coordinates, what gets kicked out is this extra little r. And if you're interested in why it's an r instead of an r squared or instead of a theta, your book goes over that. But all you have to remember is anytime you convert from rectangular coordinates to polar coordinates, dy dx or dx dy changes to r dr d theta. So a while ago, I introduced this dA at the end of the double integral, and I said that could either refer to dx dy or dy dx. So we know this could be dx dy, or it could be dy dx. Now we also know that that dA could be r dr d theta. So if we convert r dr d theta, and we know that that extra r just comes as a package deal, is that Jacobian whenever you change from x's and y's over to r's and thetas. So if you're going to rewrite a rectangular integral in terms of polar coordinates, we're still going to be integrating over the same region. We'll have to change it to look like a polar region, but we're also going to have to change the function to look like polar coordinates. We're going to have to get rid of all the x's and y's and transfer them over to r's and thetas. So the way that we're usually going to do that is with our conversion formulas. Instead of saying x comma y, I'm going to write the formulas for x and y in polar coordinates. We know that x is equal to r cosine theta. So x comma y was r sine theta. And all that's telling us to do is just convert the function over to r's and thetas instead of x's and y's. And then at the end, that dA for polar coordinates is going to be r dr d theta. All right. And just remember that that r has to be there in order for this whole thing to work. We just got to remember to put it there at the end of our integral. The last thing is that this r, this region, needs to be what we call a polar rectangle. So what's a polar rectangle? We dealt with one in the last video when we were integrating over this semicircular region that went from -1 to +1, that's semicircle. And I described that semicircle as being the region where r was trapped between 0 and 1, and theta was trapped between 0 and pi. We usually think of rectangles as being x trapped between two constants and y trapped between two constants. If we trap r and theta between two constants, we call that a polar rectangle. It does not look like a rectangle, but it is caused by taking the two variables and trapping them by constants. So because these polar rectangles don't look like rectangles, I wanted us to get a little practice with drawing a couple of them. So here we have a polar rectangle. That notation means all the ordered pairs r comma theta, such that r is trapped between 0 and 3, and that theta is trapped between -pi/6 and +pi/4. So we're talking about all the r values that are trapped between 0 and 3. That's between the origin and that third dark ring as we go out on our polar graphing paper. But our thetas are only between -pi/6 and +pi/4. All right, so -pi/6, that's down in the fourth quadrant because we're going clockwise. So that would be -pi/6 over here. All the way, we're going to swoop that through to pi/4. And we're just going to do it using radii from 0 out to 3. So from 0 to 3. So this polar rectangle is going to be this entire green pizza slice Okay, that covers all of the ordered pairs where r goes from 0 to 3 and where theta ranges from negative pi over 6 to positive pi over 4. All right, let's try to draw this one. If you feel like you're getting the hang of this, go ahead and pause the video and see if you get the same polar rectangle that I do. This time r is trapped between 1 and 2, so we're going to stay in between that first ring and the second ring. And our theta is going to range from 0 to 3 pi over 4, which is over in the second quadrant. All right, so from 0 to, so here's 0 in between that radius of 1 and radius of 2. 3 pi over 4 is our 45-degree angle in the second quadrant. But again, I'm going to stay between a radius of 1 and 2. And then I'm just going to shade in all of those values that range from 0 to 3 pi over 4. All right, so all of that area right there. So polar rectangles don't look like what we normally think of as a rectangle, but these are going to be the regions over which we're able to convert from rectangular coordinates to polar coordinates in a double integral with our special little Jacobian at the end, r dr d theta.